So we simulate multi-stage amplifier now. So in the part of multi-stage amplifier simulation, so I will be taking input signal over here. It is around 0.1 milli. So 0.1 milli is nothing but so 100 micro volts as a peak. So peak to peak it will be around so 200. So 200 micro volts. That much small signal I will be giving as the input, and I will be verifying what will be the signal over here, and I will be verifying the signal over here. So I will be taking two CROs, CRO1 and CRO2, where across the CRO1 and CRO2 I will be taking that, I will be observing the signal of this input and the signal of this output, and in the similar fashion signal of the input and signal of the output, so through which I will be calculating the gain of the first stage and the gain of the second stage. And finally I will be observing that multi-stage amplifier gain is, overall gain is, so gain of the first stage into gain of the second stage. So for that justification is, so whatever that input signal I apply, if it is let a small x, so what happening, this amplifier over here, which is exactly C amplifier which we have designed in the previous case, so where all the values are similar, bypass capacitor and coupling capacitors R1, R2, RC, RE, everything is same, and similar kind of transistor also taken, and we know what will be the resistance offered by this one also, so gain offered by this one also. Yes. So now, so there is a possibility we can change this resistance, pull-up resistance, where depending upon the gain requirement we can change it. So now for these two different CE amplifiers, so we call it as CE1 and we call this one as CE2. So the gain of the first stage is G1 is the representation for the gain of the first stage, G2 is the representation for the second stage, gain of the second stage. So now what happening is, whatever the small signal X I provide, so here this amplifier will generate a signal over here, it is around G1 times of X. So G1 times of X. So where I expect G1 times of X is like still it is not enough for me. So what I do, that G1 times of X I will be providing to the second stage, and I will be expecting that output as G2 gain times of that amplifier into the input of this one. Input of this one is G1 times of X. So overall output is G1 into G2 times of X. Means my small input signal will be multiplied by the gain of the first stage and gain of the second stage. So that much strong signal I will be getting at the output. So let us verify that that much strong signal is that much small signal are we getting at output or not through the simulation. Yes. So over here, theoretical calculations across this one is, first of all we'll calculate the gain for this stage. As we know, this is 3 kilo ohms are connected over here, 3 kilo ohms are connected, 3 parallel with the 3. It will be around 3 parallel with 3 is 1.5. There will be a pull-up resistance is 1.5 kilo ohms by, and this total network is grounded, so that dynamic resistance of the transistor itself will be considered as a pull down resistance. It is around like a 10 ohms which we designed and calculated in the first lab itself, so 10 ohms, so approximately it will give the gain around 150. Yes, so maybe like 150. So after like we have done the simulation, we observed that the gain for this stage is around 125 after we do the simulation. So let us verify the same thing is like this C amplifier is giving like the gain around 125, which are already simulated, and this case also is that same or not, let us verify. So the same connections done in the multisim, and I will be doing the simulation, right? I'm on the process of doing the simulation. I'll click on the CRO. I will be observing that input waveform. This is the input waveform and this is the output waveform. So here the signal over here, it is represented over here. This signal is this one and this signal is this one. So now I can calculate my signal strength at input of your second stage is so there is a 1 unit, 2 unit, 2.2 units. So 2.2 units into 5 is around like 5 millivolts up to here, 5 millivolts up to here. So there are around 10 millivolts and extra around 2 milliamperes. So around like millivolts, sorry. So millivolts. So there are around like 12 millivolts as the input. So it's around like it's around like 12 millivolts. I observed like 12 millivolts at the channel A, and in the channel B 12 millivolts I observed in the channel A, and in the channel B what I observed is 500 milli. So 1 2 3, it's around 3 divisions, 3 divisions into 500 milli. So 3 divisions into 500 milli, I observed like around 1.5 volts. So 1.5 volts are like 1500 millivolts, right? So from this one, if I calculate the gain, the gain is nothing but output by input. So around like a 1500 by 12, it will be around it is around like a 125. The gain around 125. So I can clearly say the gain which we got it for this stage and which already we have simulated for the CE amplifier is also 125. So this amplifier for sure it will give the gain around 125. There is no disturbance and deviation because this circuit is as it is which we have in the previous case also. So no doubt at all, the circuit gives like 125 gain. We got it around 125. But the problem with the first stage is we expect that the similar kind of module here also. Maybe the resistance is small but deviation, but we expect that gain will be almost is from if you see that the gain will be for this circuit the gain will be so 2.2 kilo ohms by from this concept pull up by pull down. So what we expect 2.25 by 10 ohms. So we expect the gain around 220 220 times, yes. So 220 times because we are keeping 2.2 kilo ohms. Yes, so here 3 parallel with 3 it's around 1.5 kilo ohms. Here like 2.2 kilo ohms, right? But the problem is it will not take like 2.2 kilo ohms into the account. So there will be, as we observe that load for this stage, that load and the pull-up resistance totally considers the total effective pull-up resistance. Here also we have to do the same job. So what we do is we have to calculate the input resistance offered by this circuit. So let us do that. Input resistance offered by this circuit. So if I do it, there will be a input resistance over here. It is like a HIE, and this network is totally shorted once we have a bypass capacitor over here. So this is what from this point to the ground there I have a HIE. So from this one I have a HIE, and there will be R1 network and R2 network is connected as it is. So once you go with AC equivalent circuit where I have to calculate AC input resistance, so that VCC is connected to the ground itself, so 0. So this also will come to the ground. So now this resistance from this point to the ground, all three comes on the parallel. So now HIE parallel with R1 parallel with R2, there will be a this much resistance we can expect from this point to the ground. So from this point also from the ground, right? So I can expect there will be a input resistance. There will be a input resistance of your second stage CE amplifier. Second stage CE amplifier. It will be of this much. So if I calculate, so 1.2 kilo ohms HIE value approximately I take it, and R2 value is around 7 kilo ohms, and R2 value, sorry, R1 value is around like 20 kilo ohms, 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 20 and this value is around 7 kilo ohms. So this total value we got it around 5.1. So this value is 5.1. So now 5.1 parallel with 1.2, if I do it into 1.2 by 6.3, right? It's around like we got it around 0.9. So it's almost equal to 1 kilo ohms, right? So we have simulated and we observed that also in the last class. Last session, where like we calculate the input resistance. We observed it will be around 1 kilo ohms. So now this entire circuit I will be removing, and the equivalent resistance of this one, it is offering the resistance of around 1 kilo ohm. I will be placing in place of this one, and I will be doing the simulation for this one. And where effective resistance of this one is not 2.2 kilo ohms, so 2.2 parallel with 1 kilo ohm. So 2.2 parallel with 1 kilo ohm, if I calculate, so 2.2 into 1 by 3.2, it is around 0.68. So now 0.68. So that effective resistance which we expect is around 220 for this circuit. Now it will be around 68. Yes, so 68. So from this one again I wanted to conclude this amplifier will offer the gain around 68 itself. So let us simulate that practically, are we getting the same or not. Let us simulate it and observe here. So this is your channel here, where it will be giving that input around 100 micro for one division. There will be two division, 200 micro as the input. So here the 200 micro as we give it is showing the same value. And coming to the output of the first stage, it will be the input of your second stage, which already monitored that in the channel A. So now I need not to monitor, but let us monitor it again. So there will be 2.2 divisions into 5 milli. So this will be the strength of 5, this will be the strength of 5, it's around 10 milli. So extra 2, it's around like a 12 millivolts or something. So as we expect like a 12 millivolts over here, like I will be getting 12 millivolts over here also, 12 millivolts over here also. So from this one in the channel A and channel B, if I calculate the gain practically we got the gain around 125. So from this one also at 12 milli, if I convert into the micro by 200, so 200, so it will be around like a 120. Sorry, it will be around 60. So we expect theoretically around 68, and practically we got it around like a 60. So now from this I can say the overall output is 200 times of. So now I can say this will be the output where I get it the value, where I get the value. So 200 micro volts is the input, so which amplifies up to here by 60 times, almost 60 times, and again it will be amplified up to here by 125 times. So 60 times into 125 times. So the gain of this stage is like that input signal will be amplified by 60 times by the first stage and 125 times by the second stage. So 60 into 125. So so it's around like 7500. So overall gain is we got it around 7500. So we have verified through CRO, and we'll be verifying through border plotter also. So here we keep a border plotter where I'm keeping a border plot. So what happening here is, so if I put it as 20 log 7500, so you will be getting the value. If I calculate this much gain in dB, if I calculate that this much gain in dB, um, 7500 dB into, so 20, it is around like 77. We got it around 77 dB. So now if I use my border plotter, so using my border plotter, let us verify that the gain is that much. So maybe you get a border plotter like this. Once you open it and once you observe the simulation across the border plotter, maybe you can observe this plot and make sure that final value it is up to, we calculated up to around 77 dB. So this value should be up to 77, more than 77. You keep it around like 100, let's suppose, so that like you can see the mid-range frequency range, the mid-range gain also. And you can bring the cursor over here and you can observe that it will be the gain around 77. So as we expected, the gain of the first stage and gain of the second stage, so for the gain of the first stage is around like 40 dB you got it. So if it is 40 dB, it's like a multi-stage, that gain of the first stage and gain of the second stage in dB it will be added. So it will be 40 plus 40, it will be 80. So all around like 80 dB, that much signal need to be amplified 80 with the strength of 80 dB. So we got it around like a 77 dB. So that because of loading on one stage with another stage. And this is the basic simulation where we observed, and for the given input we got like amplified signal.